Okay, minus 1. We can just make this one plus, since it's minus times minus. So it means we'll be left with 2, 1 minus x1, everything over v squared. I remember our v squared is gotten from here. Um, this is our v. So we'll square the whole of this. That will be our v squared. Okay, so squaring the whole of this, let me just write it out. 1 minus x1 squared plus 1 minus x2 squared plus 1. So now what to square this, the square of this. So now this is giving us our d theta dx1, just like we did here. Alright, so now the aim now is now to differentiate this one with respect to x1 again. Now so we're going to be using quotient rule that says this is equals to u over v.
Bernard, I have a question.
Yeah, what's the question?
Um, the other time you showed a graph that showed like the maximum of it.
Yeah,
I
let me
thought
check
you
for you. Let me
you
check
had
for
to
you.
find yeah. I thought you had to find this thing first,
The
the
what?
second derivative first for you to know whether
You can do anyone. The thing is, the first derivative tells you what point on the x1 and x2 plane it passes through. The
okay.
second derivative tells you what type of function it is. Maybe it's maximum or a minimizing function. You get?
Okay.
So they are like giving you two different information. It doesn't matter which one you calculate first.
Alright. Thank you.
Another question from anybody? All right, let's move on. So now differentiating this one now with respect to x1, this is our u and this is our v. Right. So now remember the quotient rule says that we're going to have this um v um then we're going to have v du minus u dv over v squared. So now it means we're going to be having this whole thing now, we'll square it again. That means that automatically will be this initial one raised power 4. Okay, we'll be doing that later, but let's deal with this top part first, since the bottom part is still easy for us to do. All right, now, so our v is this. This is our v, like we said, which is equal to this. Du, let's first find du and dv. So now differentiating u with respect to x1, we're having this u is equals to 2 1 minus x 1. If you find du the x1, okay, let's solve on this page. I was thinking of taking it to another page. So differentiating this, it's just x minus x1. If you differentiate minus x1 respect to x1, you just get minus 1. So minus 1 times 2, that's minus 2. Now let's find v. Where's this eraser? All right, so I can clean this. All right, so now I have to find v. Oh, okay, we're not finding v, we have v, sorry. So now our v is this whole stuff here, this whole thing like this. So now differentiating this one I just circled or squared or rectangled with respect to x1. So I'm differentiating this with respect to x1 now. Now, this one, if you notice, okay, let me take it gradually. Let's go to a new page. All right. So now we're having this. We're having 1 minus x1 plus 1 squared. This is our v. So how do you differentiate this with respect to x1? Now, for instance, you know that if we're differentiating, this is going to be dv dx1, which is actually going to be there's a shortcut instead of using chain rule. The shortcut is this 2 that is here, the power, you multiply it with the coefficient here. Okay, let me use a different ink. So the power of this, since this whole thing contains x1, the power of this multiplied with the coefficient. Sorry, let me mute my phone. Okay, don't need this for now. All right, so can continue. So the power of this will multiply to the coefficient, which is actually 1. So that means we're going to be having 2. Then we'll have all of this again. Then the power of this minus 1. I believe we still remember the shortcut, which is 1 minus x1. So instead of doing that chain rule we did the other time, this one is actually like faster. 1 minus x2. And you won't like take a lot of space, plus 1. Then, okay, okay, let me just use that. Then 2 minus 1, the initial power, which was 2, minus 1. I know that automatically will be giving us 1. So we can just write 1, or we just leave it like that. Then multiply it by the differential of, with respect to 1, of this whole function here. Okay, let me do a simple example so that it's not looking um weird kind of. All right, so you have something like y equals to what? X squared. So normally we say dy dx is equals to, multiply these 2 with the coefficient here, and that's going to be us 2 times x raised to power 2 minus 1, the differential with respect to x of the function that was here, of this function. I hope we get, of this one here, of this. So now this is now going to be 2 minus 1, that's just going to be x, times differential of x is going to be what? 1, and that's what? 2x. So it's the same thing that applies here, just that because this one is having so many things, you should try not to mix it up. All right, so the differential of the whole of this, so that's going to be 1 minus, mm, can I just go and do the whole of this on another page and come back? Let me do it here. Let me do it here. The differential of x1 of the whole of this 1 minus x1 squared plus 1 minus x2 squared, then plus 1. Okay, yeah, the differential of this, let me just confirm. Yeah, so now differentiating this whole function now with respect to x1, we're going to have this. No, automatically we know that this one is going to be 0. Okay, let's use a different ink. We know that this function here is going to be 0. We know that this is going to be 0 because it doesn't contain x1. Then it means what we're left with is actually this one. This is what we're left with. So we can automatically erase this one. And we just know that this is actually what we're trying to differentiate with respect to x1. So now, if we're differentiating this with respect to x1, so like the previous step that we did, that will say this 2 here we multiplied it by the coefficient here. So that's going to be 2 1 minus x1, the differential of this whole function here. I know this whole function differentiating this one with respect to 1 is going to give us this minus 1. I believe we're following. So now putting minus 1 here, it means this function here, the x1 is going to be equals to 2 1 minus x1, then this whole thing give us minus 1 times minus 1. Okay, sorry, this is not x, this is theta, the theta. Oh, was it theta? Wait, I don't think it was theta. Okay, it's v. It's not theta, it's v. Right. So our final this is going to be
Is anybody there?
I can't see anything. Stuff stop moving.
Bernard, what's up?
any.
Yeah?
Yeah, can you make me host again?
Alright, on it.
For how long did I disconnect?
Just like maybe 2 minutes.
2 minutes.
I don't
Wow.
know. Maybe
Ha,
up to
okay, because I didn't actually know that disconnected. Like I just checked now so that something went like my data. It got to the this injury. So I'll connect again. Can you make me the host so that I can share my screen? All right. So where did I stop? Can someone tell me like the last thing we did? Because I can't remember where I disconnected from.
The last tab.
Here.
Yeah.
Okay, so we
You're
got to
about
this.
writing the final answer.
Did we get to this point?
Yeah, exactly.
Hello,
Then
did we
we
get to
went
this
back
point?
into the
yeah.
previous.
Yeah.
Yes.
Putting this back into
Yeah, this is
this.
where I stop.
All right. That's fine. I thought maybe like it was very far. All right. So putting this back now into this that we just differentiated. So that's going to be 2 open bracket 1 minus x1 squared plus 1 minus x2 squared. Um, then plus 1 times the value we got from here, which is this minus 2 1 minus x1 1 minus x1. The thing about this differentiation is that sometimes you can actually make mistakes because it's, it's quite long. All right, so let's continue. So now, remember previously we solved for our value of x1. This is actually the differentiation. I've differentiated it. Okay, we've not even finished though. This is just dv dx1. No, I've not finished. Okay, we can just simplify this and then bring this minus 2 to the front here. That would be minus 4, everything multiplied by 1 minus x1. Okay. I'm coming divided x1. What's our initial equation? Mm, I'm checking for it. This v divided x1. Okay, let me just write this again. So we had this. So from here, I think I cleaned it at some point. So that's the issue I was having. V du minus u dv over v squared. So now, if you notice, we already found dv and we found du here. This is how we go for du. So now, substituting all this back into the equation, but I want to try not to make it too long. So let me point something out to us here. So at this point, are we still following?
Yeah. Yeah.
Yeah.
So at this point here, remember that our value of x1, actually we can continue, but it will just be getting too large. Our value of x1 here, previously when we calculated it, is 1. It means at x1, when x1 is equal to 1, we have either maximum or minimum. So if we substitute 1 inside here, because normally you're supposed to like finish calculating everything, you're supposed to finish calculating the whole of this before you now substitute x equals to 1, x1 is equals to 1. But because it's going to be getting quite large, we can substitute it right here. Then you notice that the whole of this equation will become 0 because this is going to be 0. We get. Do you get?
No, no, no,
Yeah.
Okay, you
no.
don't get. So what I was saying is we found out that the critical point is at x1 is equals to 1 and x2 is equals to 1.
Okay.
Now it means at that point you have either maximum or minimum. So we now have to find the second differential. I think we wrote that somewhere. Here. We have to find the
Here,
second differentials. If they
here.
are above, then we know that it's minimum. If they are above 0, if they are below 0, we know that it's maximum. So now we said we should do only this one. That this one is actually the same answer too, but we're working with only this. All right, so we now started differentiating this. Then differentiating this, we got here. We got to this point where we found the theta dx1. Then we said we use quotient rule, which is this. So
Yeah.
we did du. We found du already to be minus 2. We found dv. This dv here, we found it to be this. Remember?
Yeah.
So now we now said that we'll put it back into this equation that we're solving here. Dv dx1. We'll put it back here. And remember that x1 is equals to 1 at the maximum point. Maximum or minimum. We're not yet sure what it is. So if you put x1 here, you find out that the whole of this will go to 0. Because 1 minus 1 is 0. 0 times whatever, 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 whatever. Keep going like that. It will end up giving
Okay.
us 0.
Okay, understand.
Okay, okay, let me move on. So dv dx1 is 0. So it means that the whole of this equation now, this part rather, not this equation. Where is this palette? The whole of this part has gone to 0. So I left with the whole of, I left with just this one. I left with this one. So now we found du previously to be minus 2. Our v is actually this squared, remember? So it means it is this squared, this one times minus 2. Okay, so let's now write it. So remember that we said that the d squared theta over the x1 squared equals to v du minus u dv over v squared. And that was what we solved, that the whole of this goes to 0 already. You remember? So now it means all I left with is this v du over v squared. Okay, I want us to just take note of something, that this v here can cancel one of the v's here. So it means all I left with is what? Du over v. Do we get that? Are we still here? All right. So what do we get as our du? We solved that previously. That was -2, right? So that was -2. Now we have to evaluate v at x is equals to 1. Okay, let me write that again. So remember our v is this. Let me write the v again. Remember, I'll say our v is the whole of this. Remember. So now, instead of okay, let's just write it out again so that we don't skip too much steps. Squared minus plus squared, then plus 1. Now remember, it is all squared. This is our v. Remember. So now, substituting our x1 and what our x2 is. Remember, our x1 is what? 1. Our x2 is 1. If you substitute that here, you notice that this this part here will go to 0, because 1 minus 1 is 0. This part here will go to 0 because 1 minus 1 is 0. We're left with only this. We're left with only 1. So it means this is equal to 1 squared. Do you understand? Do you get up to this point? I hope you guys are following. Can I get feedback?
Yes, I got it.
All right. I will write this again that I just cleaned. So all we wrote was du over v, and we said it is equals to what? Minus du is equals to -2. Now what do we evaluate our v to be now? We evaluated our v to be 1, and that means that's going to be equals to what? -2. So now we're finished evaluating our d squared theta. So we're finished evaluating our d squared theta over the x1 squared, and that's equals to what? -2. Likewise, if you evaluate d squared theta over the x2 squared, you're also going to get -2. Same answer. So now, for the first variable x1 and this second variable x2, we found out that when we found their second differential, we got negative. And we said that when we get like negative for both variables, it means it's a maximum point. So it means actually the graph is going to be something like this. Since we are sure now that it's a maximum, we can be sure of how to draw the graph. x1, x2. Now at point 1, where this is point 1, this point 1, we know that it's at this point. And we know that if, for instance, since it's a maximum, we know that it's going to be somewhere up. And so we're going to be having a graph like this, a 3D graph. Do you get? So
Yeah.
that's maximum. Now you can actually find at what point it is maximum. So remember we found our x1. You know, this is um this is x1
Uh,
at point
Excuse
1.
me. Is it supposed to be 2 or 3 lines? I don't understand the graph.
The graph. Okay, I was trying to like illustrate it as like a 3D graph. It's
Okay.
not just a line. It's like a cup that is upside down. So that's why I like put a line here, like trying to show you that it's like a cup, then dotted line behind. Do we get? Um, type of graph. All right, so can we see this particular graph here? Or can we see the graph here? All right, I'm coming. Can we see the graph towards my, like almost at the center of my screen, but towards the left hand side? Are you guys there?
Yeah, I can.
So you
Yes.
can see the graph here where my cursor is.
Yeah.
Yeah, so it's this type of graph I was trying to like illustrate. It's like a 3D graph. But this maximum point here for the type of question we're trying to solve now, it means at points when x1 is 1 and x2 is 1, at this point here, if you trace it down to the xy plane, you get x1 as 1 and x2 as 1. So you can also find what value of theta is. Looking at our graph here, this maximum point here is the value of theta at the maximum, which will correspond to this place. Now, for you to find this value, you go back to the initial function. Where's the initial function again? Yeah, this initial function. Now, at what point is it maximum? Is maximum at when x1 is 1, when x2 is 1. By the time you substitute that into here, into this whole equation now, if you substitute that into this whole equation, you'll be getting at what point theta is maximum. So like this graph now, you'll be getting this peak value. You get,
Yeah.
right? So there are different types of, they are called extremums, sure. Okay, so there is no, not villain. I'm coming. So there's maximum. Now for maximum, you have that the differentials, the second differentials of every variable. You know, we have just been dealing with x1 and x2, but actually it can be multiple variable. You can have like x1, x2, x3, x4, up to xn, for instance. So now we have that the second differential of that function with respect to a variable, but we'll just use x to like illustrate that we're doing for all the variables. Now, for we to say it is maximum, it means everything must be less than 0. Take note, not equal to 0, like not less than or equal to, it must be less than. Then for minimum, you have that the differential, second differential, must be greater than 0, not equal to. Now, in such cases where one of them might be equal to 0, for instance, if you have like x1, x2, and x3, now you differentiated, you got the second differential of all those variables. If any of the variables equals to 0, for instance, maybe you did the d squared f over the x, maybe x1 squared, for instance. If it is equals to 0, and maybe the other one is positive, maybe x, let me just write it over dx2. Maybe for instance, we got it to be positive. Now, these are the only two variables in our function, x1 and x2. If x1 is 0, it's a stationary point. Remember, I said there's maximum, there's minimum. There's also stationary points. Now, the stationary point is where any of the variables is 0. Now, the idea of stationary point is this kind of graph. Can we see this type of graph over here? Am I guys there?
Yeah.
You can see this graph where my cursor is.
Yes, we
Can you see my cursor?
can see.
Okay, so this graph where my cursor is, if you notice, looking at it from this side of the graph, you see that it forms like a maximum.
Yeah.
You can see that, right? Yeah, that's almost like this type of equation I'm telling you, where the x, if you look at it from the x2 side, is okay. No, this is minimum actually. Okay, let me assume that this is negative. Where is the eraser? Let's assume that this is negative, because remember, it's when it's negative that we get maximum. So if this is negative, for instance, it means that If you look at it from this axis, x2 axis, it will look like a maximum. If you look at it from x1 axis, it will look like a straight line. That's how we're having zero. So now, looking at it from this graph, if you look at it from this side, it looks like a maximum. But if you look at it from this axis, it will look like a straight line because you only be seeing this line here. So this is like an example of stationary point, where at one point it looks like it's a plane, it's just a straight line, and here it looks like a maximum. So that's a stationary point. The stationary point can be, this one can be zero, these other ones can behave anyhow. It can be negative, it can be positive, or whatever. So that's for stationary. And there's one more saddle point. Where can I write this now? Okay. So for saddle points, now for saddle points, you have that they have alternate signs. For instance, if you are having two variables like x1 and x2, x1 can be positive, x2 will be negative, or x1 will be negative, x2 will be positive. The idea is just that they have alternating signs. So if you look at it from the x2 axis, if for instance x2 is negative, if you look at it from x2 axis, it will look like a maximum graph or a maximum curve. Then if x1 is positive, if you look at it from x1 axis, it will look as if it's a minimum graph. Let me see if I can find a graph here that illustrates that. Or let me just search. All right, can we see this where my cursor is on?
Yes, and
All right, so if you're looking at it from this angle, you see that it looks like a minimum. But if you're looking at it from this angle, it will look like a maximum. So now, if you actually find the second differential here, since it's a maximum, you'll be getting negative. If you find the second differential here, because it's a minimum, you get positive. So this is the idea of saddle surfaces. Now, if it's like multi-variable, we're just dealing with two variable. The idea is they are alternating signs. So you can have like two positive, two negative. Talking about the second differential now, you can have maybe two positive, two negative. That's if it's three variable, or two negative, then one positive. So the idea is just that they are alternating signs. Sure. All right. So that's for this example. So that solves that. Then I think our notes. Is let me see. It's these notes. All right. There was a. He went further to ask us something.
We have 2 minutes more.
2 minutes more. All right. Is the is it going to end the Zoom call? Like is that the maximum?
Yeah.
Okay, I can't find what I'm looking for though.
Is this your
Let me check
notes?
my notes.
Like our class notes?
Mm,
Bernard,
yeah.
Can you hear me? Can you hear me?
I can just call it edition
is this our class
since
notes?
it's finished my last.
Can you hear me? Can you hear me?
Yeah, I'm hearing you.
Like for this example, for the example that I just finished now,
Yeah.
it's because the two if you do the theta squared, the x1 squared, and the theta squared, the x2 squared, it
Uh-huh.
will give us one. That's why the two. Is that
It will
why the
give us
graph is like that? Is it
minus
that
two. We got minus two.
minus two? Sorry.
Minus two. Yes. So
That's
that's
why
what.
the two will give us minus two.
Yes, both will give us minus two. I know that's meaning
Okay.
that is maximum graph. That's why it's also.
Okay.
Bernard, that notes. Is it our class notes?
Yeah. Naomi's notes.
Okay.
Well, Dr. Fash, you added one question to this question, like a sub question, but I can't find it.
Wait, do you want to continue? We can create another meeting.
All right, now let's call
Eh?
it a day then. So let's call
Should
it a day then.
Now no go like
like do you even want to continue?
I guess it's fine by everybody now.
Okay.
When we continue now, now continue.
If you want to continue, you can continue.
Any,
Yeah.
what should we do?
Depends now. Have you covered like most parts? I think you've touched just
Just
this.
the same question. I don't wanted to solve like
Mm-hmm.
it's like
Then
the B part
maybe
of the
we'll
question.
have another class, another topic. Alright.
Yeah, the other one is about Lagrange something,
And that will be another class now.
Lagrange multiplier.
So I think we have 19 seconds.
We see we they do like this.
So we'll call it a day now.
All right. Anyways, this
Thank
is
you.
what I was looking for. I just remember now. This is the question here, sure. This is the big part of the question. This one. So